This concave mirror is made from expanded polystyrene, and this reflective film at a cost of 25 cents per square meter, and it is several hundred times cheaper than these mirrors which focus solar radiation to convert it into heat and electricity, and such a radical reduction in the cost of similar mirrors makes their electricity cheaper than from solar panels, or thermal and nuclear power plants.
I have already made many mirrors from expanded polystyrene for this solar station, which provided space heating of this house in the winter and heated the water of this pool in the summer during 8 years. But my solar station used similar polystyrene mirrors which formed a concave trough, while this video will show the solution to a more difficult problem when such a reflective film should form not a trough but a dish. Now I am showing another blogger's attempt to solve this problem, although we see that he used polyurethane foam instead of the polystyrene. This is his mirror, and we understand that making a quality mirror is a difficult problem, but I was able to do it, and now I will show how my mirror focuses the solar radiation to this point, which will set fire to this piece of paper. But before I got that good mirror, I made 7 unsuccessful mirrors, which helped me see my mistakes and the possibilities of correcting them. With the goal of seeing the problems and their solutions, let's look at my journey through 7 unsuccessful mirrors to this successful mirror. Now I will remind you how this unsuccessful mirror of that blogger was made. He used this hard surface with this hole, and now we see how he applies glue but only along this circumference. After that he put a reflective film and pressed it to that glue circumference. Then he used this pump, which pumped air under the film through that hole, and therefore the air pressure gave the film the shape we needed. After that he put a lot of polyurethane foam, but unfortunately the hardening of the foam is accompanied by its unpredictable expansions, which spoiled the desired shape of the mirror. Many of you have already realized that the foam needs to harden on a solid surface, and that is why I used this satellite dish. Then I put down a reflective film and stretched it out. I will put a lot of polyurethane foam here, and now we see how I did it. This was my first unsuccessful mirror, and we see that it turned out noticeably better, although it is still very far from our wishes. Now we see that it is even trying to focus solar radiation, but it is obvious that I have to make the second mirror with the addition of this circle of expanded polystyrene, whose surface roughly matches the shape of that satellite dish. The making of the second mirror also began with the actions that I placed a reflective film on the satellite dish and then covered it with polyurethane foam, but now I have added that polystyrene circle with weights. Now we see that the second mirror turned out better than the first, and it focuses noticeably better, because the polystyrene circle limited the expansion of the foam, which more evenly filled the space above the satellite dish. However, we can see that the surface of the second mirror still has many defects, for example here, where the edges of the steps of the polystyrene circle are located. That is why I decided to remove these steps, and now I will show that the polystyrene circle for the third mirror has a smooth surface without the steps. So, making the third mirror starts with preparing this reflective film, which is placed on that satellite dish and stretched. After that I applied polyurethane foam. Another difference between the third mirror and the second is that I tried to use as little foam as possible and increased the amount of those weights. This is the result of that making, and we see that the surface of the third mirror is still not ideal. Nevertheless, it already focuses solar radiation well here, and now this focus will try to set fire to this piece of paper. Unfortunately, the focus quality is not good enough to give the paper a fire, but it is enough to give it a smolder, which burns a large hole in the paper. That is why I have to make a false mirror where the foam was placed not on the reflective film but on the polystyrene circle, like this, because it seemed to me that the upper surface of the foam hardened more smoothly. Now my false mirror will try to give fire to this piece of paper, and we can make sure that it solved this task very quickly. Let's look at the quality of its mirror surface, and it is obvious that I need to improve it even more, and the idea of the following mirrors is based on laying the foam not in a continuous layer, but in similar tracks. These were the foam tracks for the fifth mirror that we see now. Using the tracks instead of a continuous foam layer makes several sense, including a high-quality mirror surface and lower cost of mirrors due to reduced the foam consumption. Now we will see how the fifth mirror ignites this piece of wood, and we understand that igniting a piece of wood is a more difficult task than igniting a piece of paper. Nevertheless, sooner or later the piece of wood gets fire. These are the foam tracks for the next mirror, and they led to this result. We can see wrinkles in these areas, and therefore I will add more tracks here on the periphery of the polystyrene circle. Now I am showing the foam tracks on the periphery that are in addition to these straight tracks. This result shows that I should increase the width of the tracks on the periphery to make these wrinkles disappear. Now we see the foam for the last mirror that we see now. But let's get back to the question, why am I researching this type of mirror and what goals should I achieve? I remind you that I am researching several types of mirrors which are a combination of expanded polystyrene and cheap reflective film. One of the problems is withstanding strong winds, and it is obvious that this mirror on a very thin polystyrene sheet can be destroyed by winds. That is why I mount it on an additional curved sheet, and I am researching a variety of methods for quickly and cheaply replacing thin mirrors after 1 or 2 year periods. This is the second option for solving the problem of strong winds, when thin mirrors are reinforced with similar ribs with a long lifespan. So, this video describes the third option for resisting winds, when dish-shaped mirrors are very rigid, unlike trough-shaped mirrors. I also remind you that our mirrors must produce very cheap thermal energy, half a cent per kilowatt hour. Achieving this goal requires that the annual cost of replacing old mirrors with new ones be less than $1 per square meter of mirror. One of the options is to use more expensive reflective films with a lifespan of 3 or 5 years, so that the cost of a mirror with a polystyrene circle is between $2 and $4 per square meter. The second option suggests using a cheap reflective film with a lifespan of 1 or 2 years, but the expensive polystyrene circle is used for many years for several mirrors. So, we must have a production line which removes an old film from the polystyrene circles and glue a new film onto them. It is obvious that I need to continue my research to answer all these questions and present the new research in my future videos. In addition, you may have noticed that the latest mirror still has several types of defects, for example these areas, which arose due to uneven application of the foam and several other causes. Also pay attention to these wrinkles which appeared after the mirror was made. This was a video 10 days after the mirror was made, but this is an early video, 7 hours after it was made, and we can notice that the wrinkles covered a smaller area. In addition, we can notice that here, in large areas of the foam, and here in the foam tracks, the mirror is of lower quality than here in the spaces between the tracks. I also remind you that I have a lot of experience with mirrors based on polyurethane foam tracks, and therefore I can predict their short lifespan. Typically, solar radiation and weather conditions will destroy the adhesion of the foam to the film after 6 or 8 months in the open air. That is why I most often made the tracks not from the foam but from acrylic glue, which forms these very thin tracks.